Alright, so let's continue with gradient boosting, and we will use the example of the housing price prediction, something that we discussed in the early stages of this whole course. So what are the data? Well, the data is basically 6 samples, and we have the size of the house and we have the price of the house. So the size of the house, this is our x, our feature, and so there is this xi here. I goes from 1 to 6, and the y is our label, which is the price of the house. What we then did is we put all of this in a graph, and we tried to force a linear model onto the graph, and this is what we did here. So we saw that this line, the linear model, doesn't go through these points. Yeah? It just goes a little bit in the middle, because it's impossible to connect these points with a straight line. So we have to sacrifice. And the sacrifice in our case, we define a cost function. The cost function would reflect how close we are to the model. And so this is a linear relationship here, Wx plus b. This is the weight and the bias. Yeah? And here we can see how to define this cost function, because basically what we're going to do is we're going to calculate the distance between the true y and the predicted y. So the true y 900 being this point here, the predicted y being on the black line. And then we're going to add them all up, square, and divide by the number of samples. And this we called the cost function. The mean squared error is the sum of all these little red lines here. We square and we divide by the number of samples. And then in order to find the best line, what we did is we minimize that cost function. Now, because we know when we minimize the sum of the squares of these red lines, we'll have the best possible line. And in order to do that, we used an algorithm called gradient descent. And basically gradient descent is a man here walking down the hill until you find the minimum of that quadratic. Quadratic because the cost function here is quadratic. Okay, so now let's see what gradient boosting is. And the last formula we saw was that f0 of x equals the sum of m equals to 1 to m of fm of x. That was the formula. Yeah? Sorry, this here will be an m. M is our target function. In our case, this would be y predict. So y predict is a sum m equals 1 to m fm x. This will be our predicted value. Then we need to define a cost function. Cost function will be quite similar to this one. And this cost function we define as half of the sum of y minus y predict squared. Yeah? So this is our cost function. Okay? And in order to find the minimum, we need to take the derivative with respect to yp, yeah, and set it to 0. So the derivative of c with respect to yp equals, the 2 goes to the front, so it's half times 2, and then times the sum, and we still have y minus yp here. The square disappeared because that's the one, and I still gotta differentiate this with respect to yp because of the chain rule, and the differential of this piece is minus 1. Okay, so dc dyp equals, this disappears, and that is minus the sum of y minus yp. Yeah. That is an important formula here that we will be able to reuse later. Alright, so now we have to initialize our model. Well, so we're going to initialize the model. So we're going to calculate this F0. Yeah. How are we going to do it? Well, it's quite simple. F0 of x, we're going to take the minimum with respect to yp, yeah, of that cost function. Okay, so we're gonna calculate this. So this sum will have 6 terms, one for each sample. So first, let us take the derivative. The derivative is going to be the same as here. It's going to be minus the sum of y minus yp. Okay? Yeah. And that means that it's going to be minus, and y for my first sample is 60. 60 minus y predict. Minus, and then we have 180 minus y predict. Minus, and all the way down to 900 minus y predict. 6 terms, and we see that the minus and the minus here is going to give a plus. 1 IP, 2 IP, 3 IP, all the way to 6 IP. Yeah, 6 YP, YP equals, and then 6 YP minus, and then the sum of all these, which is basically the sum of this whole column, is 2390, and this we're gonna set to 0. Now this is what we do when we look for a minimum. So that means that in this case, YP equals to 390 divided by 6 is 398. 398, yeah, is YP, which is basically F0. It's our first prediction. So here is going to be F0. So the first prediction means that we predict the price of 398 for all the samples. Yeah. So we fill out 398, 398, 398, 398, 398, 398. Well, that's what we get for our first estimate. And this here, there's 2 important things here. First, it is an average of the price. Yeah. And secondly, it is just a leaf. It's a single leaf of a tree. Nothing